All right, we're gonna finish up with one little short video about a special case of 1D kinematics, and that is an object that is falling. So when an object falls near the surface of the Earth, we actually have a set acceleration. And that acceleration is 9.8 meters per second squared. In other words, if I drop something, a second later, if drag isn't important, it's going to be going 9.8 meters per second. 2 seconds later, it's going to be going 19.6 meters per second. In other words, 2 times 9.8. This is true of any object in a vacuum. Okay, so a feather, the reason a hammer actually drops more quicker than a feather is because of air resistance, because of drag. But we're ignoring that right now. And in that vacuum, they would actually fall at the same pace. And we could test that if we went to the moon, which we're not going to do. Anyway, the number would be different on the moon because the gravitational pull of the moon is different. It'd be a big mess. It'd be really expensive too. All right, so a couple of things to remember about free fall. Acceleration, when we're doing these problems in kinematic, is independent of an object's mass. That seems counterintuitive to us, right? And it is because essentially it's wrong on Earth. We do have air resistance. And so that is not going to be true of anything that has significant air resistance. In other words, if it's moving quickly, moving really quickly, or if it has, sort of mass like a feather, where that can be easily overcome by air resistance. So we're thinking mostly of large, say, circular objects like cannonballs and, maybe a hammer, something like that. That acceleration is independent of that object's mass. And that acceleration is constant. It's always going to be 9.8 meters per second squared. So you can kind of get that number in your head because you'll use it a lot in these problems. So those are our free fall assumptions here, right? And if you climb to the top of a mountain, you actually get an acceleration that's a little bit less than that because it has to do with the distance to the center of the Earth's gravitational center. So that 9.8 depends on us being, around sea level. So there's a ton of assumptions we're making as we think about free fall. Now, if we think of that as a vector, we're going to put a negative sign there because we're usually going to say up is positive and down is negative. And we call that acceleration g. So you'll see that in a lot of equations. So let's draw a little quick picture of what happens in free fall. So here we have your kid brother throwing a potato in the backyard because physicists love potatoes because they're just like, what's round and generally shapeless and can represent whatever we want. Oh, it's a potato. Yeah, so we're going to throw a potato in the air. And we want to know what the plot looks like of that potato over time. So he throws it in the air. The position is at 0 initially, right? So let's see. Let's go here. Our position is initially at 0, right? So we start there. After some bit of time, it's going to reach its peak, right? So that potato floats all the way up. And then it's going to start falling back in time, falling back to the ground. One of the interesting things about free fall is that it's symmetrical. If there's no air resistance, again, which there usually is, this distance here is going to be the same as that distance there. And as it turns out, and we can sort of think about this as it falls, as it starts to fall, it's going to fall kind of slow, right? So we're going to go like that. And then it's going to get faster and faster. And we know that because it's accelerating. Its velocity downward is getting higher, right? So we can imagine that it starts to fall slow, the slope is low, starts to fall faster and faster, and it goes down. Well, since it's symmetrical, we're going to do that on this other end too. When I first throw the ball in the air, it's going to go really fast, and then as it reaches its peak, it's going to slow down. So that's what free fall looks like. It's that nice parabolic shape there. Now, velocity, we're going to start at our initial point. The slope here is really positive and high. So I've got to draw a 0 again. So this is our 0 line. Old shaky hands, Augsburger. That's our 0 line. Initially, our velocity is high and it's positive, right? Big slope. I'm throwing that ball upward. At the middle point, our velocity is actually 0, which is kind of interesting, right? It reaches that peak, and for a moment, it stops. Okay? And so in the middle, our velocity is 0. And then here, our velocity is large again. Our slope is big, but notice that it's a slope downward. So that's a negative velocity. And so our plot here actually looks like this. It's a nice linear plot because a constant acceleration, right? The slope of velocity is acceleration. So our slope here is the same the whole time. And as it happens, that slope is 9.8 meters per second. Okay, so that's what our velocity plot looks like. And then what's our acceleration plot look like? What did I just say about our acceleration? It's constant, right? So initially, it's 9.8 meters per second squared. In the middle, it's 9.8 meters per second squared, and at the end, it's 9.8 meters. As soon as it leaves your kid brother's hand, it starts accelerating downward. And so really, I should be putting this here. I'm going to draw our constant acceleration here, if I can, like this. But it's important to remember that this is our 0 line here. So that's 0. And that's 0. That this is actually a negative acceleration. It's accelerating downward. As soon as it leaves your hand, as soon as it's in what we call free fall, it's accelerating in the negative direction. All right, so those are some plots for free fall. And we'll do some more practice in class.